Good day, welcome to today's lesson. This week we begin looking at data structures in GIS or GIS data structures. So again, we want to start with first of all looking at a definition of data structure. So when we talk about data structures, what we mean is this is the format of how your data is stored on the computer. Alright, so data structures are not something that we would normally see as an end user while we use the data within a particular software platform. But the data structure, this is how your data is organized and stored within a computer so that you can recognize it either as raster or vector. Alright, so we know that firstly the data must be scanned or digitized. So if you get your data in, for example, a paper format, you have to convert it into that digital format before you can integrate it with your GIS. So once you've done that digitization or converted into that digital format, you need to make room for editing. Alright, because any conversion always, as we've said before in previous lesson, propagates error. So you want to make time for editing. Once your editing has been completed, then you will convert your data into that final form where you can use it in your GIS software or GIS application. Alright, that final form is what we would refer to as our raster or vector. Okay, now the choice of the data structure can affect both your data storage volume and processing efficiency. Now I would have mentioned in previous lectures before, typically you find your raster data model tends to require larger amounts of storage space than the vector. But on the flip side, you find that the raster data tends to facilitate faster and more efficient processing speeds than the vector, because the vector's data organization or data structure tends to be more complex than the raster. Alright, so again, what is the data structure? As we said, that is the format in which the data is stored on a computer, and it is that data structure that is used as information that the computer would need in order to reconstruct the spatial data model into digital formats. In other words, the data structure that is stored on the computer is used by the computer to reconstruct it into what we will see on the computer screen, either represented as that vector model, such as points, lines, and polygon features, or that raster model, which would be our layer made up of a series of cells. So we need that data structure to complete that reconstruction. Alright, so all of this as we go through the next few slides is really just to reinforce that concept. So we have our data models represented on this image here. We see the same features, points, lines, and area features, represented both in vector format and as raster format. Okay, so this is our data model. Now let's look on this side. Follow with me carefully so we can understand data structure. So we start any GIS with the real world. From the real world, we will have a map representation of the features on the real world, and once we convert this map into a digital format, either through scanning. So if we scan, please note a scan will produce a raster data model. So this is what it would look like. So this is our data model. If we digitize, for example, using a digital table where we trace the features to get points, lines, and polygon features that will produce a vector model. Now for each of these, they are stored differently on the computer. So a raster data set will be stored on the computer with our data arrangement looking something like this. For example, binary coding. We see our data or binary values represented, organized here in rows and columns, whereas our vector, the organization of our data structure is very different. Okay, we see a series of numbers. In a later lesson you learn a little bit more about that to understand what those numbers mean. And so these are our data structures. So again, we are reminded that the data structure is how the data is stored on the computer to allow the computer to reconstruct the data into the appropriate data models. Okay, so in summary, the data model, this is how the data is represented. For example, how it looks. So that would be raster or vector. And your data structure, this is how the data is stored on the computer. Alright, let's look a little bit at vector data models and structures. So we would always again start off by reminding ourselves what that data model looks like. So we're talking about vector. So we know that our vector data models are based on elements that are represented in the form of points, lines, or polygons. Remember, those polygons are our area features whose locations are known. Alright, so all objects represented in the vector data models are determined by XY locations in coordinate space. So for example, so that's pretty easy to understand with regards to a point. So a point will have an XY location, but what we're saying is even lines and polygon features that are defined, whose outer perimeter are defined by lines, every point along those lines is represented by an XY location. Right, so that is why we can say all objects are represented by XY locations in coordinate space. Alright, our points use single coordinate pairs to represent location of entities that have no dimension. So in other words, it's just a point. When we're talking about location, it's just a point. So it's just a location. So you have no other dimensions such as length or width or height or anything like that. That is not represented in an XY location. Additionally, we take note as well that our linear features are represented as arcs. So linear features or line features, what do we mean by arcs? Let's take a look at this now. So lines typically have a starting point and an ending point. When in using the vector data model. Alright, those starting and ending points, we call them nodes, and in between those points we can have other intermediate points, and we refer to them as vertices. Alright, where we have area entities or polygon entities, they must be represented by closed polygons. So remember, I mentioned in the previous slide where a polygon will be defined by a line defining the outer boundaries of the polygon. Alright, if that line is not closed, meaning that the start of the line and the end of the line meet each other in the same location, it cannot be represented as a polygon or area feature in ArcGIS. Once it remains open, it is merely a line. Okay, so we were talking about these nodes. So here, for example, we have a line. That entire line is what we would refer to in GIS as an arc. The entire line is an arc. We have a start node here and an end node here, so they are both represented by nodes. That line can be made up of different segments, and where they join, we would refer to that as a vertice. or vertex, sorry, vertices is plural. Okay, but bear in mind, what we need to understand is several segments can make up one line feature. For example, it might be a road, and you know that a road sometimes may be interrupted by intersections or bends in the road, but the entire line would represent the line feature. Additionally, when we were talking about polygons here, we continue. We also know that when polygons have an interior region, okay, remember that polygon within a polygon, the polygons must be completely enclosed within another polygon. Alright, so we're moving on. So what we want to do here now is touch very briefly on a little history of that vector data model. And that history takes us back to what we call a spaghetti data model. So the spaghetti data model, this was an early version of the vector data model, but what distinguishes it from the modern version of the vector data model, is the fact that there is no spatial relationship between those lines, points, or polygon features. That is what is characteristic about vector data model. A vector data model has topology. In some of the slides to come, we will see what topology means. In the spaghetti data model, each line is recorded separately. That is, the computer does not recognize line features as being spatially related to any other line. So in other words, if the lines cross each other and there's intersection, spaghetti data model could not recognize that. So therefore what we say is there is no inherent topology, or in other words, spatial relationship between those features. So spaghetti data model, spatial relationship is absent there. So what we just described, what would that look like? So here, let us assume these are the same features represented using the spaghetti data model, and the features represented using vector, which shows topology. So we have the same lines. Notice the labels are the same, but what is different? We see, if I've circled in red the problem areas there for you. For example, we see lines crossing over each other. We see gaps in lines where the points should have connected to close the polygon. Here we have what we call an overshoot. Here is another gap. So remember what we said, where the lines are not closed, it is not a polygon. Alright, so these are some errors in the data, but because it's represented as spaghetti data model, there is no inherent spatial relationship. Now if we were to represent those same lines using the vector data model, which has topology, we see that all those lines now and points and end nodes have been neatly connected to each other. So now the computer, with the inherent data structure stored on the computer, can now recognize these various features as being related to each other. For example, recognizing that this polygon P2 is adjacent to polygon P3 and P1, or that these lines are connected to each other, etc. So what are the problems associated with the spaghetti data model? Polygons may not close, making it impossible to identify regions inside or outside the polygon. The spaghetti data model, as we said, does not recognize spatial relationships. In GIS, we said that if a polygon is not closed, it is not recognized as a polygon, but it is simply only a line. Another problem with spaghetti data model, because of the absence of that inherent spatial relationship information, there is limited spatial data analysis capability. Alright, so because spatial relationships are not recognized, spatial analysis cannot be applied using spaghetti data model. So let's talk about this topology, this particular characteristic of the GIS data model that we are talking about. So topology is applied using the modern vector data structure. That topology is actually organized into the data that is stored on the computer so that the computer can recognize those relationships. Note, topology is not applied to spaghetti data model. Topology is the organization of spatial relationships between the features in GIS. So in other words, topology, this is the way that the GIS knows. It knows about the spatial relationships. What are some of these spatial relationships? For example, it can tell us where features are in relation to each other. It can tell us what parts of different features are shared. For example, points can be shared by lines. Lines can share points. Lines can be related to polygons. Polygons related to lines, and so on. It can tell us how the features are shared. For example, is it shared through connectivity? Connectivity would be associated with line features. For example, when we represent network features in the form of lines, such as let's say stream networks, river networks, pipeline features, electrical lines, etc. Topology ensures that information is not necessarily repeated. For example, if we can look at adjacency to explain that. All right, so what we are looking at here are the properties of topology. It's very important for you to know these properties. So for example, each of these properties, when you look at the description and then we would look at some visuals, we will see how in those arrangements how we are avoiding the unnecessary repetition of features. For example, adjacency refers to the sharing of boundaries. So you can have two properties right alongside each other sharing one boundary, but because we know that they are adjacent to each other and they're two distinct properties, it's not necessary for you to have more than one boundary line between them. Just imagine you have two properties and you have a wall between them. Is it necessary to have two separate walls? No, you only need to have one wall. Then connectivity refers to the sharing of nodes. For example, where we have road intersections, that intersection can be represented by a shared node. And then another property of topology is containment, where we can represent polygons within a polygon, and we would have looked at an example of this already, a lake within a county. So here we have some visuals. So we talked about adjacency. Imagine imagine polygon A and polygon B represent your property boundaries. The chain is actually the line. So we see that there is one shared line between A and B. Connectivity, we have three lines. Those are the chains. We have A, B, and C. And note that all three lines are connected by one node. So here we can actually identify a spatial relationship and say that A, B, and C are connected by node 1. So that is our described spatial relationship. And containment, polygon B is contained within polygon A. And these are examples of spatial relationships using the vector data model that can represent features in the real world. So what might this look like on our computer now? Here at the top we have our data model. We have several features. We have lines such as A3, A1, A2, etc. A5 is this long line here. We have some polygons. This is polygon A, polygon B, C, and E represents the outside boundary. Okay, we can actually identify coordinates because all of our features are located on a graph. We have our x-axis and we have our y-axis. So these coordinates are what are going to be used in our data structure organization to describe location and relationships of features to each other. And this is what we are looking at beneath here. These tables represent the data structure for these vector features represent organized in the computer, right? For example, let us look at our polygon topology. Again, we have our polygons listed A to E. Let's look at the first one, the spatial organization of polygon A. So we know this is polygon A. It tells us that polygon A is defined by arcs, or in other words lines, A1, A5 and A3. Let's find those. We have A1, A5 and A3. Note, we do not include A4 because A4 is not closed to another, is not connected to another node in order to close this polygon. So it is essentially just a line, a dangling there. Polygon B. Polygon B is defined by A2, A5. There's a 0 in there somewhere. That is most likely an error. I don't know if it's this. I can't see quite clearly. A6. A6 is a line. I believe that's also an error because you can't clearly see A6 other than a label. Alright, and A7, look, we include A7 as well. Alright, so if you look, you could clearly see that polygon C is actually contained within polygon B, but we include line A7 as a boundary line for polygon B, because what you have to do is really visualize this area here as though like it's a donut and a hole has been cut out of it, and then you took another piece of dough and you stuffed C right inside there. So that extra piece of dough was actually not connected to B, but you just fitted it in there. Alright, let us look at some arc topology. Let's look at the arcs connected to node 1. So we have node 1. Node 1 is connected to line A1, line A3 and A4. And similarly, you can go through all of these and find the spatial relationships yourself. Let's look at the arc topology or the line topology. Let's start with A1. And now remember I said that all arcs begin and end with a node. So we have a start and end node here. So A1 starts with node 1 or N1 and it ends at N2. Notice we have a node here. Remember what those nodes are, right? Those are intermediate nodes, right? Notice it also tells us that in relation to that line we have a left polygon and a right polygon. So why do we say the left polygon is E and the right is A? I'll tell you why. Because by telling us which is our start node and our end node, they've given us direction. So just imagine yourself walking along this line from N1 to N2. As you walk, E would be on your left, A will be on your right. And lastly, let's look at one example from our coordinate data, and let's see how we read it. A1, we're going back to that line. It tells us our start node is at this coordinate. It's at 40x, 60y. It tells us we have an intermediate coordinate at 70x and 60y. That's our intermediate. And our end coordinate, note, 70x and 50y. So that's how this data is organized in the computer. But remember what I said, typically you would not actually see that when you're interacting with the data. So what are the advantages of our vector data structures? The vector data structures, they provide good representation, good visual representation of the different phenomena as points, lines, and polygon features. Typically, it's much more appealing than the raster representation as well. It gives better resolution in terms of level of details of the feature. Remember, we talked about geometry, location, shape, size, so it gives better resolution in that sense. Better level of detail and accuracy, locational accuracy, shape, size, as we mentioned. Advantage is that topology can be completely described, that spatial relationship, and that can represent connectivity and interrelationships of your features. Additionally, it can provide fast retrieval, updating, and generalization of your graphics and attributes. So, for example, if you have any errors of lines or points on the screen, it's very easy for you to go in and edit on the screen, and as your map is edited, it automatically updates the attribute table, and vice versa. If you need to, let's say, a classification you need to change in the attribute table, it automatically updates on your map. So that's another advantage of this data structure. But it's not perfect. It has some disadvantages. What are the disadvantages? For example, it's difficult to manage because the data structure is complex. Remember when we looked at the two of them side by side in a previous slide? The raster data structure is essentially numeric, is very well organized, and it's simple, whereas the vector data structure is it's much more complex, and you have to understand what you're reading in order to interpret. Vector data structure as well, the combination of several vector polygon maps or polygon and raster maps through overlaying creates difficulty. So in other words, the more of those layers that you have in vector that you have to overlay, is the more complex it becomes, and it makes your analysis even more complex. Vector also requires a fair amount of processing capacity in order to carry out analysis. So it requires a lot of hardware and software resources to carry out analysis because of the complexity of the data structure. It requires a fair amount of resources for display and plotting, or printing in other words, and that can be very expensive. Typically, technology for this, as I said, is because of the amount of resources it needs, it could be very expensive. And last point there, your spatial analysis and filtering within polygons are impossible due to the hard boundaries. What do we mean by that? Remember, for example, in vector, a polygon is defined by a line, and you can only assign one value to the interior of that polygon. In other words, if you have other features occurring within there, you can't represent it. It's impossible to represent using the vector data model. Okay, that is why there are times you may choose to represent your data using raster rather than vector. Now we're going to have a brief introduction to the raster data structure, but that will be continued in the following week's lesson. So the raster data model, what does it look like? As we would have seen before, you have regular cells in a grid pattern that are evenly spaced in an X and Y direction. Alright? In other words, rows and columns. The cells have a characteristic cell dimension or cell size, which is what we refer to as resolution. If you recall, when we talked about resolution before, resolution is usually an indication of level of detail. Precision of the data set, and hence the positional accuracy is also affected by the cell dimension. So a rule of thumb you want to remember is that where you have high resolution, you can assume greater accuracy of your data is available. And remember, when we talk about cell size and cell resolution, the smaller the size is the higher the resolution. So positional accuracy, you need to remember this one as well. Positional accuracy is typically no better than approximately half the size of the cell. Because remember, the a point feature, for example, can fall anywhere within that cell size. So the larger the cell is, the greater your risk of error. The smaller it is the less your risk of error. And if the feature is more than half, I beg your pardon, if this feature that you're interested in is less than half the size of the cell, you would not be able to see it or pick it up at all. So here is a little visual to try to put that into context for you. So we have 3 different resolutions represented here. We have a 10 meter, 5 meter, and 1 meter. Note, with the 10 meter resolution, so the colors represent the level of detail that you can get. In other words, numbers of features you can identify. So the 10 meter, you can only identify the green feature. With the 5 meter, you can now identify 2 features, the green and the blue. Each of these 4 blocks in this space is actually 5 square meters. Now when you break it down further, each of these blocks here represent 1 square meter. You now have 3 colors represented, which means you can actually identify 3 features. Okay, and what you're looking at here, follow the red line, we have resolution increasing in this direction. Okay, now typically the cell coordinates or the location assigned to the cell, typically we would define that at the center of the cell. Okay, each cell represents a given area on the ground, in other words a given location, and is assigned a value that is applied to that cell. Those values tend to be numeric in nature. Alright, so what those colors we are looking at is an interpretation of those numeric values. Alright, and here we have a generic structure of a grid. It's basically the same thing that we've been looking at before, and you remember we talked about X and Y values. So we have our cells organized as rows. Our rows we read across. If we read across, we represent those, we interpret those along the x-axis. Our columns run vertically, and we would interpret those along our y-axis. Okay. At this point, I want to say thank you for joining me for today's lesson. Please refer at this point to eClassroom for this week's activity. Thank you.